Welcome to the Foundation of Machine Learning course. In today's lesson, we will introduce the concept of machine learning and explore the various stages of the machine learning lifecycle. We have a lot of ground to cover, so let's dive in and move on to the next slide. Machine learning, or ML, has emerged as a transformative force in the world of technology, revolutionizing the way we approach data and decision making. At its core, ML is a branch of artificial intelligence that focuses on enabling computers to learn and improve from experience without being explicitly programmed. This powerful concept has opened up a world of possibilities, allowing us to tackle complex problems and drive innovation across various industries. As we delve deeper into the realm of machine learning, we discovered that it encompasses three main categories, each with its own unique characteristics and applications. These categories are supervised learning, unsupervised learning, and reinforcement learning. Supervised learning is a type of ML where the algorithm learns from labeled data, much like a student learning from a teacher. In this approach, the algorithm is presented with input data along with the corresponding correct output, allowing it to learn the relationship between the two. This makes supervised learning ideal for tasks such as image classification, spam email detection, and predicting housing prices. Some of the most widely used algorithms in this category include decision trees, random forests, and support vector machines. On the other hand, unsupervised learning deals with unlabeled data, where the algorithm must discover hidden patterns and structures on its own. This type of ML is particularly useful for exploratory analysis, customer segmentation, and anomaly detection. Clustering algorithms, such as k-means and hierarchical clustering, are commonly employed in unsupervised learning scenarios. The third category, reinforcement learning, takes inspiration from how humans and animals learn through interaction with their environment. In this approach, the algorithm learns by receiving rewards or penalties for its actions, continually refining its decision-making process. Reinforcement learning has been the driving force behind breakthroughs in robotics, gaming AI, and autonomous vehicles. To harness the power of machine learning effectively, it's crucial to understand the ML lifecycle. This iterative process involves several key stages, starting with data collection and preprocessing. Once the data is ready, the next step is to select an appropriate model and train it using the prepared data. Evaluation and tuning are essential to optimize the model's performance before it can be deployed into a production environment. Even after deployment, ongoing monitoring and maintenance are necessary to ensure the model continues to perform at its best. In conclusion, machine learning is a powerful tool that has the potential to transform the way we approach data and solve complex problems. By understanding the different types of ML and the life cycle of an ML project, organizations can leverage this technology to drive innovation, improve efficiency, and gain a competitive edge. As we continue to explore the vast landscape of machine learning, one thing is certain: the possibilities are endless, and the future is bright for those who embrace this transformative technology. Machine learning, or ML, has emerged as a game-changing subset of artificial intelligence, AI, that is revolutionizing numerous industries, from healthcare and finance to marketing and transportation. ML is being leveraged to automate tasks, improve efficiency, and drive innovation. At its core, the goal of machine learning is to develop models that can identify patterns within data and make predictions or decisions without being explicitly programmed. The power of machine learning lies in its ability to learn from data. Unlike traditional computing, where programmers explicitly define the logic and rules for a system to follow, ML algorithms are designed to learn patterns and relationships from the data they are exposed to. This approach enables ML models to adapt and improve over time, making them highly versatile and applicable to a wide range of problems. To achieve this, machine learning employs various learning algorithms that help fit models to the data. These algorithms can be broadly categorized into three main types: supervised learning, unsupervised learning, and reinforcement learning. Each type has its own strengths and is suited for different kinds of tasks and data. Supervised learning algorithms learn from labeled data, where the desired output is known. The algorithm tries to find a function that maps the input data to the correct output labels. This type of learning is commonly used for tasks such as image classification, spam email detection, and predicting housing prices. Unsupervised learning, on the other hand, works with unlabeled data. The algorithm's goal is to discover hidden patterns or structures within the data without any guidance. This is particularly useful for tasks like customer segmentation, anomaly detection, and exploratory data analysis. Reinforcement learning takes a different approach, inspired by how humans and animals learn through interaction with their environment. In this paradigm, an agent learns to make decisions by receiving rewards or penalties for its actions. The agent's objective is to maximize the cumulative reward over time. Reinforcement learning has been successfully applied in areas such as robotics, gaming AI, and autonomous vehicles. Regardless of the learning algorithm employed, the machine learning lifecycle follows a similar pattern. It begins with data collection and preprocessing, followed by model selection and training. The trained model is then evaluated and fine-tuned to optimize its performance. Once the model meets the desired performance criteria, it can be deployed into a production environment, where it continues to be monitored and maintained to ensure optimal performance. In conclusion, machine learning is a powerful tool that enables computers to learn from data and automate tasks without explicit programming. By leveraging different learning algorithms and following the ML lifecycle, organizations can harness the potential of ML to solve complex problems, improve decision-making, and drive innovation. As we continue to explore the vast possibilities of machine learning, it is clear that this technology will play a pivotal role in shaping the future of various industries and our daily lives. Machine learning has emerged as a transformative technology, enabling computers to learn from data and make predictions or decisions without being explicitly programmed. To understand the vast landscape of machine learning, it's essential to explore the different categories of learning algorithms that form the foundation of this field. Machine learning methods are generally classified into three broad categories based on the nature of the learning algorithms: supervised learning, unsupervised learning, and reinforcement learning. Each category has its own unique characteristics, strengths, and applications. Supervised learning is the most common category of machine learning. In this approach, the algorithm learns from labeled data, where both the input data and the corresponding correct output are provided. The goal is to learn a function that maps the input data to the correct output labels. Supervised learning is widely used for tasks such as image classification, sentiment analysis, and predicting customer churn. Popular algorithms in this category include decision trees, random forests, support vector machines, and logistic regression. Unsupervised learning, on the other hand, deals with unlabeled data. The algorithm's objective is to discover hidden patterns, structures, or relationships within the data without any guidance or predefined labels. Unsupervised learning is particularly useful for exploratory data analysis, customer segmentation, anomaly detection, and dimensionality reduction. Clustering algorithms like k-means and hierarchical clustering, as well as dimensionality reduction techniques like principal component analysis, PCA, are commonly used in unsupervised learning scenarios. The third category, reinforcement learning, takes a different approach inspired by how humans and animals learn through interaction with their environment. In reinforcement learning, an agent learns to make decisions by receiving rewards or penalties for its actions. The agent's goal is to maximize the cumulative reward over time. Reinforcement learning has been successfully applied in areas such as robotics, gaming AI, autonomous vehicles, and resource management. Popular algorithms in this category include Q-learning, SARSA, and policy gradient methods. It's worth noting that deep learning, which has gained significant attention in recent years, is sometimes considered a separate category of machine learning. However, deep learning is essentially a specific implementation of learning algorithms, primarily based on artificial neural networks with multiple layers. Deep learning has achieved remarkable success in various domains, including computer vision, natural language processing, and speech recognition. While deep learning can be applied to supervised, unsupervised, and reinforcement learning tasks, it is particularly well suited for handling large, complex, and unstructured data. In conclusion, understanding the different categories of machine learning is crucial for leveraging the power of this technology effectively. Supervised learning, unsupervised learning, and reinforcement learning each have their own strengths and are suited for different types of problems and data. Deep learning, while sometimes considered a separate category, is a powerful implementation of learning algorithms that has revolutionized many fields. By grasping the characteristics and application of these categories, practitioners can choose the most appropriate approach for their specific machine learning projects and drive innovation across various industries. Supervised learning is one of the most widely used and successful approaches in machine learning. At its core, supervised learning relies on labeled or annotated data, where each data point is associated with one or more target variables. These target variables serve as the ground truth or the desired output that the algorithm aims to predict. The labeled data used in supervised learning can be thought of as a teacher guiding the algorithm, providing examples of the correct answers. By exposing the algorithm to a sufficient number of labeled examples, it learns to generalize the patterns and relationships between the input features and the target variables, enabling it to make predictions on new, unseen data. Supervised learning can be further divided into two main problem types: classification and regression. The choice between classification and regression depends on the nature of the target variable. Classification is applied when the target variable is qualitative, meaning it has discrete outcomes or categories. For example, predicting whether an email is spam or not spam is a binary classification problem. Other examples include sentiment analysis, positive, negative, or neutral, disease diagnosis, presence or absence of a condition, and image classification, identifying objects in images. Popular classification algorithms include decision trees, random forests, support vector machines, and logistic regression. On the other hand, regression is used when the target variable is quantitative, representing continuous numeric values. Regression problems aim to predict a specific value rather than a category. Examples of regression problems include predicting housing prices based on features like square footage and location, estimating sales revenue based on marketing spend, or forecasting stock prices. Common regression algorithms include linear regression, polynomial regression, and support vector regression. The supervised learning process typically involves several steps. First, the labeled data is collected and preprocessed, ensuring its quality and compatibility with the learning algorithm. Next, the data is split into training and testing sets. The training set is used to fit the model, allowing it to learn the patterns and relationships in the data. The testing set is then used to evaluate the model's performance on unseen data, providing an unbiased estimate of its generalization ability. During the training phase, the algorithm iteratively adjusts its internal parameters to minimize the difference between its predictions and the actual target values. This process is guided by an objective function or loss function, which quantifies the model's error. The goal is to find a set of parameters that minimizes the overall error across the training examples. Once the model is trained, it can be used to make predictions on new, unseen data. The model's performance is typically assessed using various evaluation metrics, such as accuracy, precision recall, an F1 score for classification problems, and mean squared error, mean absolute error, and R squared for regression problems. In conclusion, supervised learning is a powerful paradigm in machine learning that leverages labeled data to train models capable of making accurate predictions. By understanding the difference between classification and regression problems and following the supervised learning process, practitioners can develop models that solve a wide range of real-world problems, from spam email detection and sentiment analysis to housing price prediction and sales forecasting. As the availability of labeled data continues to grow, supervised learning will remain a crucial tool in the machine learning toolkit, driving innovation and transforming various industries. Unsupervised learning is a fascinating branch of machine learning that focuses on discovering hidden patterns, structures, and relationships within data without the guidance of labeled target variables. Unlike supervised learning, where the algorithm learns from explicitly labeled examples, unsupervised learning algorithms are tasked with inferring patterns solely based on the intrinsic features of the dataset. One of the key challenges in unsupervised learning is the absence of known outcomes or ground truth labels. This means that the algorithm's performance cannot be directly validated against predefined correct answers. Instead, the focus shifts to exploring the data, identifying inherent groupings or clusters, and uncovering meaningful association among the features. Unsupervised learning is primarily used for exploratory data analysis, where the goal is to gain insights and understanding from the data without a specific prediction task in mind. It helps uncover the underlying structure of the data, identify anomalies or outliers, and reduce the dimensionality of high-dimensional datasets. There are several common algorithms used in unsupervised learning, each with its own strengths and applications. Clustering. Clustering algorithms aim to group similar data points together based on their features. The goal is to partition the data into distinct clusters such that data points within a cluster are more similar to each other than to points in other clusters. Popular clustering algorithms include k-means and hierarchical clustering. Clustering is widely used in customer segmentation, anomaly detection, and image segmentation. Association mining. Association mining algorithms discover interesting relationships or association among items in a dataset. The most well-known application is market basket analysis, where the goal is to identify products that are frequently purchased together. Association mining helps uncover patterns like customers who buy product A are likely to also buy product B. The a priori algorithm and its variants are commonly used for association mining. Dimensionality reduction. High-dimensional datasets can pose challenges in terms of computational complexity and data visualization. Dimensionality reduction techniques aim to reduce the number of features while preserving the essential information and structure of the data. Principal component analysis, PCA, and TSNE, T distributed stochastic neighbor embedding, are popular dimensionality reduction methods. Dimensionality reduction is useful for data compression, visualization, and as a pre-processing step for other machine learning tasks. The unsupervised learning process typically begins with data collection and pre-processing, ensuring that data is clean, consistent, and in a suitable format for analysis. Next, the appropriate unsupervised learning algorithm is selected based on the specific goals and characteristics of the data. The algorithm is then applied to the data set, and the resulting patterns, clusters, or associations are interpreted and evaluated. Evaluating the quality of unsupervised learning results can be challenging due to the lack of ground truth labels. However, various metrics and techniques can be used to assess the coherence and validity of the discovered patterns. Silhouette analysis, for example, measures the compactness and separation of clusters. Domain expertise and data visualization also play crucial roles in interpreting and validating the results. In conclusion, unsupervised learning is a powerful approach in machine learning that enables the discovery of hidden patterns and structures within data without relying on labeled examples. Through techniques like clustering, association mining, and dimensionality reduction, unsupervised learning provides valuable insights and facilitates exploratory data analysis. As the volume and complexity of data continue to grow, unsupervised learning will remain an essential tool for uncovering meaningful patterns and driving data-driven decision-making across various domains. Reinforcement learning is a fascinating paradigm in machine learning that takes inspiration from how humans and animals learn through interaction with their environment. In this approach, a program, known as an agent, learns to perform a task by taking actions and observing the resulting rewards or feedback from the environment. At its core, reinforcement learning is a reward maximization problem. The agent's goal is to learn a policy, which is a mapping from states to actions, that maximizes the cumulative reward over time. This is achieved through an iterative process of exploration and exploitation, where the agent balances the need to gather new information about the environment with the desire to leverage its current knowledge to obtain rewards. To understand the mechanics of reinforcement learning, let's explore its four key elements. Agent. The agent is the program or algorithm that learns and makes decisions. It is responsible for perceiving the state of the environment, taking actions based on its policy, and updating its policy based on the received rewards. Environment. The environment represents the domain or the problem space in which the agent operates. It defines the states, action, and rewards that the agent can observe and interact with. The environment can be either fully observable, where the agent has complete information about the state, or partially observable, where the agent has limited information. Action. Actions are the decisions or choices made by the agent at each step. The set of possible actions depends on the specific problem and the agent's capabilities. For example, in a game-playing scenario, the action could be moves or strategies, while in a robotic control problem, the actions could be motor commands. Reward. Rewards are the feedback signals provided by the environment to the agent based on its actions. Rewards can be positive, indicating desirable behavior, or negative, indicating undesirable behavior. The agent's objective is to maximize the cumulative reward over time, which guides its learning process. The reinforcement learning process typically follows a cycle of observation, action, and reward. At each step, the agent observes the current state of the environment and selects an action based on its policy. The environment then transitions to a new state and provides a reward signal to the agent. The agent uses this information to update its policy, aiming to improve its decision-making in future interactions. There are several popular reinforcement learning algorithms, each with its own strengths and variations. Q-learning. Q-learning is a value-based algorithm that learns a Q function, which estimates the expected cumulative reward for taking an action in a given state. The agent selects actions based on the Q values, aiming to maximize the long-term reward. Policy gradient methods. Policy gradient methods directly optimize the policy parameters based on the gradient of the expected cumulative reward. These methods aim to find the optimal policy without explicitly estimating the Q values. Actor-critic methods. Actor-critic methods combine the strengths of value-based and policy-based methods. They use a critic to estimate the value function, and an actor to optimize the policy based on the critic's estimates. Reinforcement learning has found application in a wide range of domains, including robotics, autonomous vehicles, game playing, and resource management. It has achieved remarkable successes, such as mastering complex games like chess and Go, and has the potential to revolutionize decision-making in various industries. In conclusion, reinforcement learning is a powerful approach in machine learning that enables agents to learn through interaction with their environment. By understanding the key elements of reinforcement learning and exploring the various algorithms, practitioners can harness its potential to solve complex decision-making problems and drive innovation in diverse fields. As research in reinforcement learning continues to advance, we can expect to see even more groundbreaking application and achievements in the future. Machine learning has emerged as a transformative technology, enabling organizations to extract valuable insights and make data-driven decisions. However, developing effective machine learning solutions can be a complex and iterative process, especially when dealing with diverse application areas. To streamline this process and ensure the development of optimal solutions, it is essential to follow a structured approach known as the machine learning lifecycle. The machine learning lifecycle provides a framework for managing the end-to-end process of building, deploying, and maintaining machine learning models. By adhering to this lifecycle, teams can navigate the complexities of machine learning projects, ensuring that the resulting solutions are robust, reliable, and aligned with business objectives. While there may be some variations depending on the specific context and requirements, the machine learning lifecycle generally consists of 7 key steps. Data gathering. The first step involves identifying and collecting relevant data from various sources. This may include internal databases, external APIs, or IoT devices. The goal is to gather a sufficient amount of high-quality data that is representative of the problem domain. Data preparation. Once the data is collected, it needs to be prepared for analysis. This step involves cleaning the data, handling missing values, and addressing inconsistencies. Data preparation ensures that the data is in a suitable format for further processing and modeling. Data wrangling. Data wrangling, also known as data munching, involves transforming and restructuring the data to make it more amenable to analysis. This may include tasks such as feature engineering, where new features are created from existing ones, or data normalization, where the data is scaled to a consistent range. Data analysis. In this step, exploratory data analysis is performed to gain insights into the data's characteristics, patterns, and relationships. Statistical techniques and data visualization tools are used to uncover trends, identify correlations, and detect anomalies. This step helps in understanding the data and formulating hypotheses for modeling. Model training. With the prepared and analyzed data, the next step is to train machine learning models. This involves selecting appropriate algorithms, splitting the data into training and validation sets, and fitting the models to the training data. The goal is to learn the underlying patterns and relationships in the data. Model testing. After training the models, it is crucial to evaluate their performance on unseen data. This step involves using the validation set, or a separate test set, to assess the model's accuracy, precision, recall, and other relevant metrics. Model testing helps in identifying overfitting, underfitting, and determining the model's generalization capabilities. Deployment. Once the models have been trained and tested, they are ready for deployment into production environments. This step involves integrating the models into existing systems, creating APIs for model inference, and setting up monitoring and logging mechanisms. Deployment ensures that the models can be used to make predictions or decisions in real-world scenarios. It's important to note that the machine learning lifecycle is an iterative process. Often, insights gained during one step may necessitate revisiting previous steps to refine the approach or incorporate new findings. This iterative nature allows for continuous improvement and adaptation to changing requirements. Furthermore, the machine learning lifecycle doesn't end with deployment. Ongoing monitoring, maintenance, and updates are essential to ensure the models remain accurate and relevant over time. Regular retraining with new data, performance monitoring, and model versioning are key practices to maintain the effectiveness of deployed machine learning solutions. In conclusion, the machine learning lifecycle provides a structured approach to developing optimal machine learning solutions. By following the 7 key steps of data gathering, preparation, wrangling, analysis, model training, testing, and deployment, organizations can navigate the complexities of machine learning projects and deliver value-driven solutions. Embracing the iterative nature of the lifecycle and ensuring ongoing maintenance and updates are crucial for the long-term success of machine learning initiatives. In the realm of machine learning, the journey towards building effective solutions begins with a crucial first step: data gathering. This stage lays the groundwork for the entire project, as the quality and quantity of the collected data directly impact the performance and reliability of the resulting machine learning models. Data gathering involves identifying, accessing, and integrating relevant data sets that align with the problem at hand. It requires a deep understanding of the domain and a clear definition of the project's objectives. By carefully selecting and curating the appropriate data, we set the stage for the subsequent steps in the machine learning lifecycle. One of the challenges in data gathering is the diverse range of formats in which data can exist, from structured databases and flat files to unstructured sources like text documents and images. The data landscape is vast and varied. Each format requires specific techniques and tools for extraction and integration, making data gathering a multifaceted task. Structured data, typically stored in relational databases or spreadsheets, offers a well-defined schema and organized rows and columns. This type of data is often easier to process and analyze, as it adheres to a predefined structure. Examples of structured data include customer records, financial transactions, and sensor readings. On the other hand, unstructured data poses unique challenges. Text data, such as customer reviews, social media posts, and email communications, lacks a rigid structure and requires advanced techniques like natural language processing, NLP, to extract meaningful insights. Similarly, image and video data demand specialized algorithms and preprocessing steps to convert the visual information into a format suitable for machine learning models. The quantity of data is another critical factor in data gathering. Machine learning algorithms thrive on large amounts of data, as they can learn more robust and generalizable patterns. However, the pursuit of quantity should not compromise quality. It is essential to strike a balance between having sufficient data to train effective models and ensuring that the collected data is accurate, relevant, and representative of the problem domain. Data quality is paramount in machine learning. Noisy, incomplete, or biased data can lead to suboptimal or even misleading results. Therefore, data gathering must be accompanied by rigorous data validation and cleaning processes. This involves identifying and handling missing values, removing duplicates, and addressing inconsistencies. By investing time and effort in data quality assurance, we lay a solid foundation for the subsequent stages of the machine learning lifecycle. Moreover, data gathering should consider the ethical and legal implication of collecting and using data. Privacy concerns, data protection regulations, and fairness consideration must be taken into account. It is crucial to obtain necessary permissions, anonymize sensitive information, and adhere to relevant guidelines and standards throughout the data gathering process. In conclusion, data gathering is the critical first step in developing machine learning solutions. It involves identifying, accessing, and integrating relevant data sets that align with the project's objectives. The diverse formats of data, ranging from structured databases to unstructured sources like text and images, require specific techniques and tools for extraction and integration. The quantity and quality of the gathered data directly impact the effectiveness of the resulting machine learning models. By ensuring data quality, considering ethical and legal implications, and striking a balance between quantity and relevance, we set the stage for successful machine learning projects. As we move forward in the machine learning lifecycle, the foundation laid by effective data gathering will guide us towards building robust and reliable solutions. In the journey of building effective machine learning solutions, data preparation emerges as a crucial step that bridges the gap between raw data and actionable insights. While data gathering lays the foundation by collecting relevant data sets, data preparation takes it a step further by refining and transforming the data into a format that is suitable for analysis and modeling. Almost all data, regardless of its source or format, requires some level of preparation before it can be fed into machine learning algorithms. The extent and complexity of data preparation may vary depending on the nature of the data and the specific requirements of the project. However, investing time and effort into this step is essential to ensure the accuracy, reliability, and performance of the resulting models. To effectively prepare the data, a deep understanding of its characteristics, structure, and quality is paramount. This understanding can be gained through a process of exploration, which involves delving into the intricacies of the data and uncovering its underlying patterns and relationships. Exploratory data analysis is a key technique in data preparation. It involves using statistical methods and visualization tools to gain insights into the data structure, format, and quality. By examining summary statistics, data distributions, and correlations, we can identify potential issues, such as missing values, outliers, or inconsistencies that need to be addressed before proceeding with modeling. Understanding the general trends and patterns within the data is crucial for making informed decisions during the preparation phase. Visualization plays a vital role in this process as it allows us to identify relationships, detect anomalies, and uncover hidden insights. Tools like scatter plots, histograms, and heat maps can help in visualizing the data from different perspectives and identifying potential areas of interest. Correlation analysis is another important aspect of data preparation. By examining the relationship between different variables, we can identify features that are strongly related and may have a significant impact on the target variable. This information can guide feature selection and engineering efforts, where we focus on the most relevant and informative attributes for our machine learning models. Outliers, or data points that significantly deviate from the norm, require special attention during data preparation. Outliers can have a substantial impact on the performance of machine learning algorithms, as they can skew the results and lead to biased or misleading conclusions. Identifying and handling outliers appropriately, either by removing them or treating them as separate cases, is essential to ensure the robustness and reliability of the models. Data preparation also involves addressing data quality issues, such as missing values, inconsistencies, and formatting errors. Missing values can be handled through various techniques, such as imputation, where missing values are estimated based on the available data, or deletion, where records with missing values are removed. Inconsistencies, such as conflicting or duplicate records, need to be resolved to maintain data integrity. Formatting issues, such as inconsistent date formats or text encoding, should be standardized to ensure compatibility with the machine learning algorithms. Furthermore, data preparation may involve feature engineering, where new features are created based on the existing ones. This process can help in capturing complex relationships and providing additional information to the machine learning models. Feature engineering requires domain expertise and creativity to identify meaningful combinations or transformation of the original features. In conclusion, data preparation is a critical step in the machine learning lifecycle that lays the groundwork for successful modeling and analysis. It involves exploring and understanding the structure, characteristics, format, and quality of the data. Through techniques like exploratory data analysis, correlation analysis, and outlier detection, we gain valuable insights into the data and identify potential issues that need to be addressed. By handling missing values, inconsistencies, and formatting errors, we ensure the integrity and reliability of the data. Feature engineering further enhances the data by creating new, informative features. By investing time and effort into data preparation, we set the stage for building accurate, robust, and reliable machine learning solutions that can drive meaningful insights and decision making. In the realm of machine learning, data wrangling emerges as a critical step that bridges the gap between raw, unprocessed data and the development of high-performing models. It is the process of cleaning, transforming, and consolidating data into a format that is suitable for analysis and modeling. By investing time and effort into data wrangling, we lay the foundation for building accurate, reliable, and robust machine learning solutions. The importance of clean data cannot be overstated. Machine learning models are only as good as the data they are trained on. If the input data is noisy, inconsistent, or contains errors, the resulting models will be suboptimal and may lead to inaccurate predictions or misleading insights. Therefore, data wrangling is a crucial step in ensuring the quality and integrity of the data before it is fed into the modeling process. Data wrangling involves a series of activities aimed at selecting and transforming variables to create a coherent and consistent data set. It requires a combination of technical skills, domain knowledge, and attention to detail to navigate the complexity of data manipulation and refinement. One of the key aspects of data wrangling is scaling and transforming variables. Scaling involves adjusting the range and distribution of numerical features to ensure that they are on a similar scale. This is important because many machine learning algorithms are sensitive to the scale of the input features. Techniques like normalization and standardization are commonly used to scale the data, bringing the values within a specific range or ensuring a zero mean and univariance. Transforming variables involves applying mathematical functions or operations to create new features or modify existing ones. This can include logarithmic transformations to handle skewed distributions, one-hot encoding for categorical variables, or feature interactions to capture complex relationships between variables. The goal of variable transformation is to represent the data in a way that is more conducive to modeling and can potentially improve the performance of the machine learning algorithms. Another crucial aspect of data wrangling is handling missing values. Missing data is a common occurrence in real-world datasets and can pose significant challenges for machine learning models. Strategies for dealing with missing values include deletion, where records with missing values are removed, or imputation, where missing values are estimated based on the available data. The choice of approach depends on the nature of the data, the extent of missing values, and the specific requirements of the project. Data wrangling also involves identifying and removing duplicates and invalid or erroneous data points. Duplicate records can introduce bias and skew the results of the analysis, while invalid data points, such as outliers or errors, can have a significant impact on the performance of machine learning models. By carefully examining the data and applying appropriate techniques, such as deduplication algorithms or outlier detection methods, we can ensure the integrity and reliability of the dataset. Outliers and noise are other important considerations in data wrangling. Outliers are data points that significantly deviate from the norm and can have a disproportionate impact on the models. Noise refers to random or irrelevant variation in the data that can obscure the underlying patterns and relationships. Detecting and handling outliers and noise requires a combination of statistical techniques, domain expertise, and careful judgment. Techniques like z-score analysis, interquartile range, IQR, method, or density-based clustering can be employed to identify and remove outliers and noise from the dataset. In conclusion, data wrangling is a critical step in the machine learning lifecycle that focuses on cleaning, transforming, and refining data for optimal modeling. By investing time and effort into data wrangling, we ensure that the input data is of high quality, consistent, and suitable for analysis and modeling. Through activities like scaling, transforming variables, handling missing values, removing duplicates and invalid data, and detecting outliers and noise, we create a solid foundation for building accurate and reliable machine learning models. Data wrangling requires a combination of technical skills, domain knowledge, and attention to detail. But the rewards are significant in terms of improved model performance and actionable insights. As we progress in the machine learning lifecycle, the efforts put into data wrangling will pay dividends in the form of more robust and effective solutions. As we progress through the machine learning lifecycle, we arrive at the pivotal stage of data analysis. This is where the rubber meets the road and the actual model building process begins. Data analysis is the cornerstone of creating effective and reliable machine learning solutions, as it involves evaluating and selecting algorithms, searching for optimal model parameters, developing models, and assessing their performance. The first step in data analysis is to evaluate and select the most appropriate algorithms for the problem at hand. This requires a deep understanding of the different types of machine learning algorithms, their strengths and limitations, and their suitability for the specific task. Whether it's a classification problem, a regression task, or an unsupervised learning scenario, choosing the right algorithm is crucial for achieving optimal results. Once the algorithms are selected, the next step is to search for the best model parameters. Model parameters are the knobs and levers that control the behavior and performance of the algorithms. They can have a significant impact on the model's ability to learn from the data and make accurate predictions. Techniques like grid search, random search, or Bayesian optimization can be employed to systematically explore the parameter space and identify the optimal configuration. With the algorithms and parameters in place, the focus shifts to developing the actual models. This involves training the selected algorithms on the prepared and wrangled data, allowing them to learn the underlying patterns and relationships. The training process is iterative, with the models being fed the data and adjusting their internal parameters to minimize that discrepancy between the predicted and actual outcomes. It's a delicate balance between fitting the training data well and generalizing to unseen instances. As the models are developed, it's essential to evaluate their performance using appropriate metrics and validation techniques. This is where the true test of a model's effectiveness lies. Performance evaluation helps us assess how well the models are learning from the data and how accurately they can make predictions on new, unseen instances. Metrics like accuracy, precision, recall, F1 score, or mean squared error are commonly used to quantify the model's performance, depending on the nature of the problem. Cross-validation is a powerful technique used in data analysis to assess the model's performance and robustness. It involves splitting the data into multiple subsets, training the models on a portion of the data, and evaluating their performance on the held-out subset. This process is repeated multiple times, with different subsets used for training and testing to obtain a more reliable estimate of the model's performance. Cross-validation helps in identifying overfitting, where the models perform well on the training data but fail to generalize to new instances. By iteratively evaluating and refining the models, we gain insights into their strengths and weaknesses. We can compare the performance of different algorithms, experiment with various parameter configurations, and assess the impact of different feature sets. This iterative process allows us to identify the most promising candidates and select the final model that strikes the right balance between performance and generalization. At the end of the data analysis phase, we have a clear understanding of the final model type and the optimal parameters to be used for training on the full dataset. This knowledge is crucial for the subsequent steps in the machine learning lifecycle, where the selected model will be trained, validated, and deployed to tackle real-world problems. In conclusion, data analysis is the cornerstone of model building in machine learning. It involves evaluating and selecting algorithms, searching for optimal model parameters, developing models, and assessing their performance. By leveraging techniques like cross-validation and iterative refinement, we can identify the most effective models that can learn from the data and make accurate predictions. The insights gained during data analysis lay the foundation for the subsequent steps in the machine learning lifecycle, ultimately leading to the development of reliable and impactful solutions. As we move forward, the knowledge and experience gained from data analysis will guide us in making informed decisions and building models that can drive meaningful insights and drive business value. Model training is the culmination of the data analysis phase, where the selected algorithms and optimal parameters are put to the test. It is the process of leveraging the full power of the available training data to build robust and reliable models that can make accurate predictions on unseen data. Once the most promising algorithms and the best combination of parameters have been identified through rigorous data analysis. It's time to train the final model. This is where the rubber meets the road, and the model is exposed to the entire training dataset. The goal is to allow the model to learn from the data, capture the underlying patterns and relationships, and generalize well to new instances. During the training process, the model iteratively adjusts its internal parameters to minimize the discrepancy between the predicted and actual outcomes. It's a delicate dance between fitting the training data well and avoiding overfitting, where the model becomes too specialized to the training examples and fails to generalize to unseen data. Techniques like regularization and early stopping can be employed to strike the right balance and prevent overfitting. As the model is trained, it gradually improves its performance, learning from the vast amount of data it is exposed to. The training process can be computationally intensive, especially for large dataset and complex models. However, with the advancements in hardware and distributed computing, model training can be accelerated and scaled to handle even the most demanding datasets. Once that training is complete, the final model is stored for future use. This stored model becomes a valuable asset, ready to be deployed and used for making predictions on new, unseen data. Whether it's classifying images, predicting customer churn, or recommending products, the trained model encapsulates the knowledge and insights learned from the training data. It's important to note that model evaluation would have already been performed during the data analysis phase, as part of the model selection process. Techniques like cross-validation and performance metrics would have been used to assess the model's effectiveness and guide the selection of the final model. This early evaluation ensures that the chosen model has the potential to perform well on unseen data. However, it's crucial to continuously monitor and evaluate the model's performance even after deployment. As new data arrives and the world evolves, the model's performance may degrade over time. This phenomenon is known as concept drift, where the underlying patterns and relationships in the data change, rendering the model less effective. Regular monitoring and periodic retraining can help mitigate concept drift and ensure that the model remains accurate and relevant. In addition to monitoring, it's also important to establish a feedback loop between the model's predictions and the actual outcomes. By comparing the model's prediction with the ground truth, we can identify areas for improvement and gather valuable insights for model refinement. This feedback loop enables continuous learning and adaptation, allowing the model to evolve and improve over time. In conclusion, model training is the critical step where the selected algorithms and optimal parameters are applied to the full training dataset to build robust and reliable machine learning models. It's a process of allowing the model to learn from the data, capture the underlying patterns, and generalize well to unseen instances. The trained model becomes a valuable asset, ready to be deployed and used for making predictions on new data. While model evaluation would have been performed during the data analysis phase, continuous monitoring, periodic retraining, and establishing a feedback loop are essential for maintaining the model's performance and relevance over time. As we move forward in the machine learning lifecycle, the trained model will serve as the foundation for driving insights, making informed decisions, and solving real-world problems. Model testing is a crucial step that ensures the reliability, accuracy, and performance of the developed models. It is the process of rigorously evaluating the trained models using a separate and dedicated test dataset to assess their ability to generalize and make accurate predictions on unseen data. During the early phases of model development, evaluation is typically performed using either an evaluation set or cross-validation techniques. These methods provide valuable insights into the model's performance and guide the selection of the best algorithms and parameter configurations. However, it's important to note that validation data used in these early evaluations cannot be relied upon to generate unbiased performance metrics. This is because the validation data is often used to refine the model parameters, leading to a potential bias towards a specific validation set. To obtain a truly unbiased assessment of the model's performance, a separate and dedicated test set is employed in the model testing phase. This test set is carefully curated and kept entirely separate from the training and validation data. It serves as a final arbiter, providing an independent evaluation of the model's effectiveness and generalization capabilities. When conducting model testing, several relevant metrics are used to quantify the model's performance. The choice of metrics depends on the nature of the problem and the specific goals of the project. For classification tasks, metrics such as accuracy, precision, recall, F1 score, and area under the ROC curve are commonly used. These metrics provide a comprehensive understanding of the model's ability to correctly classify instances into their respective categories. For regression problems, where the goal is to predict continuous values, metrics like mean squared error, root mean squared error, mean absolute error, and R squared are employed. These metrics quantify the model's ability to accurately predict the target variable and capture the goodness of fit between the predicted and actual values. In addition to these standard metrics, domain-specific evaluation measures may also be used depending on the application. For example, in recommender systems, mean average precision and normalized discounted cumulative gain are used to assess the quality of the recommendations generated by the model. It's important to thoroughly analyze the results of model testing and interpret the metrics in the context of the problem at hand. A model with high accuracy may still have limitations or biases that need to be understood and addressed. Techniques like confusion matrices, precision recall curves, and error analysis can provide deeper insights into the model's performance and help identify areas for improvement. Model testing also plays a crucial role in detecting and mitigating issues like overfitting and underfitting. Overfitting occurs when the model becomes too complex and starts to memorize the training data, leading to poor generalization on unseen instances. Underfitting, on the other hand, happens when the model is too simple and fails to capture the underlying patterns in the data. By evaluating the model's performance on the test set, these issues can be identified and addressed through techniques like regularization, model simplification, or increasing model complexity. In conclusion, model testing is a vital step in the machine learning lifecycle that ensures the reliability, accuracy, and performance of the developed models. By using a separate and dedicated test set, unbiased evaluation metrics can be obtained, providing a true assessment of the model's effectiveness. Thorough analysis of the test results, interpretation of the metrics, and identification of potential issues like overfitting and underfitting are crucial for refining and improving the models. As we move forward, the insights gained from model testing will guide the deployment and application of the models in real-world scenarios, enabling data-driven decision-making and driving business value. The final and most rewarding step in the machine learning lifecycle is model deployment. It is the culmination of all the hard work and expertise that goes into developing, training, and testing a machine learning model. Deployment is the process of integrating the trained model into a production environment, making it accessible and usable for real-world applications. Deploying a machine learning model is a critical step that bridges the gap between the controlled development environment and the live production system. It is the moment when the model's true potential is realized, and its predictions and insights can be leveraged to drive business value and inform decision-making. The deployment strategy depends on the specific application context and the requirements of the project. One common approach is to expose the model as an API, application programming interface. By creating a well-defined API, the model can be seamlessly integrated with other software applications, allowing them to consume the model's predictions and incorporate them into their own workflows. This enables a modular and scalable architecture where the machine learning model can be accessed and utilized by multiple systems and services. Another deployment approach is to directly integrate the model into existing applications or systems. This involves embedding the model's functionality within the application's codebase, allowing it to make prediction and provide insights in real time. This approach is suitable when the model needs to be tightly coupled with the application logic and requires low latency responses. Regardless of the deployment strategy, it is crucial to ensure the model's performance, reliability, and scalability in the production environment. This involves careful consideration of factors such as data pipelines, infrastructure provisioning, and monitoring mechanisms. The deployed model should be able to handle the expected volume and velocity of data, respond to requests in a timely manner, and gracefully handle any errors or exceptions. In many real-world scenarios, the environment in which the model operates is dynamic and evolving. The data distributions, user behavior, and business requirements may change over time, affecting the model's performance and relevance. To address this challenge, continuous monitoring and updates to the deployed model are essential. Monitoring involves tracking key performance metrics and gathering feedback on the model's predictions and outputs. This can include metrics such as prediction accuracy, response times, and resource utilization. By closely monitoring these metrics, any degradation in performance or unexpected behavior can be quickly identified and addressed. When the monitoring process reveals that the model's performance is deteriorating or no longer meeting the desired standards, updates to the model become necessary. This may involve retraining the model with fresh data, fine-tuning its parameters, or even exploring alternative algorithms or architectures. The goal is to adapt the model to the changing environment and ensure its continued effectiveness and relevance. Updating a deployed model requires a well-defined process and infrastructure. It involves versioning the model, managing the transition between different versions, and ensuring backward compatibility where necessary. Techniques like A/B testing and canary deployments can be employed to gradually roll out updates and minimize the risk of disruption to the production system. In conclusion, model deployment is the final and most impactful step in the machine learning lifecycle. It is the moment when the trained model is brought to life in a production environment, accessible and usable for real-world applications. The deployment strategy, whether through APIs or direct integration, depends on the specific context and requirements of the project. Ensuring the model's performance, reliability, and scalability in the production environment is crucial. In dynamic environments, continuous monitoring and updates to the deployed model are necessary to adapt to changing conditions and maintain its effectiveness. As we embrace the power of machine learning, successful model deployment enables organizations to harness the full potential of their data, drive innovation, and stay ahead in an ever-evolving landscape. As we conclude this lesson, I want to express my genuine hope that you found the material both informative and engaging. It has been a pleasure presenting this content to you, and I sincerely wish you all the best in your future endeavors. Thank you for your attention and participation.